Good morning, everybody. I want to welcome you to another Earth to Class program. This week we're featuring Alex DeSherbinin from CIESEN. CIESEN stands for the Center for Integrated Earth System Information, and it's a center within the Columbia Climate School. Lamont is also within the Columbia Climate School. CIESEN attempts to harness cutting-edge geospatial technologies to support integrated analysis of the human environment system and to empower decision-making through collaborative research, teaching, and data production, stewardship, and dissemination. CIESEN values inclusivity, it's impactful and interdisciplinary teamwork, and it builds bridges among academics, practitioners, decision makers, and communities. Today, we're going to focus on some of the CIESEN products that could be used for teaching. So, without further ado, I want to welcome Alex. Alex, I've got you as co-host, so if you need to share the screen, you should be able to do that.
Great, Mike. Yeah, I was trying to remember when we first met. I'm sure it's at least 15 to 20 years ago.
Well,
So
Roberta was still the director.
then it was 24 years ago, maybe. I joined in 1999, rose through the ranks, and now I'm director of CIESEN. And so it's a pleasure to be with you all today. And if you see me look over occasionally, it's because I have you all on my screen over here, and I'm got my PowerPoint in front of me. So CIESEN, I'm going to talk today about a few things. I'll give a little history of CIESEN in a moment, but we'll talk about some of our major programs, talk a bit more in depth about some of our population mapping work, climate-related work, some top, open science, participatory science topics. I'm not going to go into great detail on the research outcomes, but we can talk more about climate migration, which is my particular area of focus, how climate change may influence redistribution of population in the United States and around the world, mostly around the world, but I also do talk to journalists and others who are particularly interested in what's going to happen in the US, especially in light of recent major hurricanes and fires in LA. So CIESEN is actually, as of last year, we changed our name from Center for International Earth Science Information Network. So you'll see I may have missed one or two logos in the bottom corner here, but that was our old name. We recently changed the name to Center for Integrated Earth Systems Information, the main reason being that nobody really remembered our longer name, and it didn't really make sense to be both a center and a network. So we believe this Center for Integrated Earth Systems Information emphasizes the way that humans are integrated in the Earth system. And so that's really why we have this new name. We started, though, in 1989, actually as a pork barrel project in Michigan. I guess a congressman at the time wanted to get some of that NASA money up to his district in Saginaw, Michigan. It started as a consortium, and in about a decade after its founding, it was realized that it wasn't really going to survive after the congressman passed away. Unfortunately, wasn't going to survive in Saginaw, Michigan, so it better connect itself to a larger university. 10 universities put out for bid, and Columbia University was the one that had the most compelling bid. So we moved to Columbia in 1998, and I joined 1 year after CIESEN moved here. I had actually been familiar with CIESEN before. I'd been to some meetings in Saginaw and had interacted with the director at that time. The director under whom I served the longest, which is Bob Chen. He succeeded Roberta Miller. Anyway, so we have offices on the Lamont campus. Mike is a frequent guest, and we love to have him come to our brown bags and things. We're mostly a social science group, so it's a little misleading to say that we're an Earth systems group. But the reason, again, that I emphasize this integrated aspect is we really do focus a lot on how humans interact with the environment. So this is the website, which we recently also revised, and you can go and sort of if you type in CIESIN in Columbia or just that acronym, you'll find us, and you can certainly search and find things there that may be of interest. We had, in the process of transitioning our website over the last year, we did have to kind of stop supporting some things that may have been more specifically targeted at educators. But if you go to research and publications and resources, you will find some things that may be of relevance to educators. So I'm going to start talking about some of our major programs and where this sort of will be the standard slide format when I talk about a program. And then when I talk about individual data sets or activities, you will no longer see this little box in the upper right-hand corner. So that's the sign that I'm talking about something that's a funded project at CIESEN that we're managing. So CIESEN's, I would say about 60% of our budget or more comes from the NASA Socioeconomic Data and Application Center. So sometimes people just conflate us and they think that we're CIESEN is CDAC and CDAC is CIESEN. That's not quite true. CIESEN is an independent, center within the climate school of the Columbia University, whereas CDAC is a funded project that we manage under contract with NASA. And it provides the data that put people in the pixels. So this idea, and I'll talk a little bit more about what that means in a moment. But NASA is known not only for its amazing space travel, but you may be aware that NASA provides a lot of the Earth science data through remote sensing instruments. So they fly a lot of satellites and they download a lot of data, and those data go into archives. So we're one of 12 different archives. They're called Distributed Active Archive Centers, or DACs, and we're one of the 12 DACs, but we're the kind of the square peg that doesn't quite fit in the round hole, in the sense that we provide the ground level understanding of what's going on through compiling data on a global level around the world to come up with a consistent picture of what's happening on the ground. And I'll give you some examples of that in a few minutes. Excuse me. So we have more than 300 data sets, 14 terabytes. A lot of this is kind of eye-glazing stuff that you don't need to know about, but we do use we do get used a lot by people in these different disciplines. And we have been very active in areas of applied science like disasters, air quality, environmental justice concerns, things of that sort. So why did CDAC even get formed? Why did NASA decide to fund something that seems a little bit outside of what you might consider to be the normal areas that NASA is concerned about? Well, the reason was that some people with some foresight back in the 1990s, when they were starting what was called Mission to Planet Earth, said, well, the Earth is not just about physical processes, and this was maybe even before people were talking about the Anthropocene, meaning the new geologic era where humans are the dominant force on the planet. So maybe people weren't talking about the Anthropocene, but it was becoming increasingly clear that humans were a dominant force on the planet. And just taking pictures from space was not going to give you the full picture of what's going on the ground. So there was this landmark report by the National Research Council where the idea was, let's put people in those pixels. Pixels meaning those little grid cells that remote sensing imagery comes out as. If you've seen, most remote sensing images, they're pixelated, they're little squares. So let's put people in those pixels. And that's been a consistent theme. About 3 or 4 years ago, I co-authored this article with some, actually now it's going on 5 or 6 years ago, with some colleagues, where we revisited the question of people in pixels and kind of updated the latest science to look at how both the remote sensing imagery and the ancillary or other data that are available to work with remote sensing imagery and the tools that are available have evolved in the 20 or so years since People in Pixels was published. More recently, NASA has come out with an Earth Science to Action strategy, and this strategy has also affected how we're doing our work and what we're thinking about. So a big focus now is less on basic science and understanding, let's say, how humans interact in the environment, that's all important. But they want much more to be able to actually model the planet in a coherent way and in a consistent and comprehensive way, and to develop tools and applications that actually lead to action on the ground, so that the earth science data are actually used. We've done extensive citation analyses to look at what people who publish in peer-reviewed literature talk about or what they write about when they use our data. So we did a survey of 75 different articles, and this is a word cloud that just say that a lot of people are interested in climate change. A lot of people are interested in urban who use our data. A lot of people are interested in things like energy, pollution, quality, health, air quality, environmental, this and that. And you kind of see the cloud and how the different keywords that are highlighted. So we have 5 mission areas under CDAC. Those mission areas basically have changed a little bit over the last 25 years that I've been with CDAC. I currently manage the CDAC, so I'm not only director of CIESEN, but I manage the single biggest project that we have, the CDAC. And we divided up our work in different areas, like around population and demographics, around climate change, around hazards, around poverty and food security, and around environmental sustainable development, which is where a lot of our indicator work is. This cloud of maps basically shows some examples, like this is a social vulnerability index for the United States. So it's essentially the population that has greater vulnerability to climate impacts, for instance, in the darker blue areas. There's a gridded data set that takes the subnational infant mortality data for the whole world. There's another data set that does GDP and grids it globally. And I'll talk a bit about our flagship data product in a moment. But these 3 are examples of data that are derived from censuses, surveys, from socioeconomic research of various types, from economic data and things. But we also do a lot with remote sensing data. So this is an elevation data set. This is another one that looks at areas that are drying and wetting according to a satellite remote sensing instrument called GRACE. And you can see, for instance, Greenland and parts of the Amazon and parts of the Middle East have dried considerably over the period of record. In this case, I think it's from 2002 to around 2016. And basically, the idea was to look at how the total water volume between glaciers, rivers, surface water bodies, and underground aquifers change using gravity as a measurement device. And that's how the NASA scientists were able to derive these changes in total water volume. But some of them do reflect climate change, like the loss of ice on Greenland. And I think also you could say part of the drying in the Indian subcontinent is also due to climate impacts. And so loss of water volume there, a lot of over abstraction of water resources from deep wells and shallow wells in India to feed the growing population. Other data sets, and these 2 over here, represent sort of mashups of satellite remote sensing and socioeconomic data. So this is a human footprint that measures the degree that humans are affecting the environment, with yellow areas being more so. And then this is also one that mashes up satellite data with demographic data for India. Our core product, though, our flagship, has been this product that was developed back in 1994 to 95. The one time I went to Saginaw, Michigan, was for a workshop where they were developing this data product. It was really quite a revolution. And you kind of say, well, what's so revolutionary? Well, what they did was they took data that were available at administrative unit level, like census units, and they gridded that whole data product all those census units, all those what we call vector units, sorry, there's an automatic advance that I'm not sure how to change. So they gridded all these census units and made them into equal area grid cells. The original data set was available at about 10-kilometer resolution. We then went to 5-kilometer resolution with GPW2, and then GPW3 and 4, and now 5. It's a 1-kilometer resolution grid cell. And you can see one thing that's improved over time is the number of units that are used to construct this data set. These two gentlemen here are the sort of fathers or grandfather, as it were. Walter Tobler has passed away, but basically who created the methodology to spread the population within grid cells. And it's essentially an equal area approach to population mapping. So why do you do this? Why grid data sets that are in a native vector format? Well, the problem with vector formats is those units vary in size. So they can be very large, like counties in the US are much larger out west than they are on the East Coast. Census tracts are probably also a lot larger in the Rocky Mountains in the Midwest than they are in New York City. So if you just take those native resolution data and then try to do things like add up the total population that's in a certain watershed or in a certain mountain chain or within such distance of coast, you're basically getting bits and pieces of census units that don't match the geographies. So to grid everything, you actually are eliminating that problem, and you have a much easier time processing as well. It makes processing a lot faster. So one of the things you'll notice is a lot of our biggest projects are, some of our larger projects are basically spin-offs. So this is a spin-off where we worked with Meta to develop a gridded population data set that is a significantly higher resolution. It should be written here. I think it's basically the units are like something like 100 square meters. So they're 10 times the resolution of the 1-kilometer data set that I described before, GPW. And what they did was they took our GPW data, gridded population of the world, and they allocated the population to areas that are built up based on satellite images, Maxar images as it happens, at very high spatial resolution. These are like 50 centimeter pixels. And then they aggregate those pixels up to 100 meters. But basically, a place is either built up or it's not built up. And you can see that from the remote sensing imagery. Apparently, when they processed globally the Maxar imagery, they shut down, they used a series of their servers out in Mountain View or wherever in California, and the local power company phoned them up to make sure everything was okay because they were drawing so much energy just processing all that remote sensing imagery. Other derivative products. This is another example of a global gridded. So the HRSL, as good as it is not fully global. There's quite a lot of the world covered, but it's not completely covering the world. So the other products that do cover the world is this one. It's called Global Human Settlement Layer. This is just the built up area. So this is using another source of remote sensing imagery, Sentinel data. And they basically, if you go back to 1975, you can see for some of these cities like Sao Paulo or New York, how they've grown over time. And this is 2014, the latest time slice for this data set. And then using these built up layers, we also worked with this group in Italy, in ISPRA, they're a European Commission organization called JRC. We worked with them to map the population onto these built up areas. This is the new data product that basically gives you points and polygons for every urban area in the world, basically pretty much every urban settlement. So there's almost 125,000 urban settlements that are mapped. And for each one, we give you the population from 1975 to 2030 in 5-year increments. So if you want to map where people are in the world, this is a good example of a product that takes those gridded and other data sets and makes it into something that people might need for various mapping or cartography purposes, or they might need it for various analytical purposes. I helped develop this data set working with a colleague, and this is an example of a mashup of both demographic data and remote sensing data. And what we did was we took data on things like the Subnational Human Development Index. Those data are only available at like province or state level and for each country in the world. And so we also had child dependency ratios because one of our data products, the GPW, has population by age and by sex. And so we could actually calculate for every grid cell the number of children that 0 to 14 compared to the working age population. And typically younger age structured populations, if you look at populations with very broad basis to the population pyramid, are often poorer because their population growth rates are still rapid, and their sometimes infant mortality rates are also high in those areas, and so people are compensating for high infant mortality by having more kids. So that's sort of part of demographic transition theory, right? That as nations develop, they tend to have fewer kids. So we also combine with these data sets, these socioeconomic data on the built-up area I mentioned earlier, and then nighttime lights. And we also did a look at the slope in nighttime lights. Is it getting brighter? Is it getting dimmer? And that's this product here. We're about to release a version 1.1 of this data product that corrects a few issues that we found as people started using this data product. So we think it's getting better over time. Another kind of line of work that we got very involved in, partly due to a former staff member, Deborah Bulk, we got very involved in looking at the low elevation coastal zone and the populations and land areas in these low elevation coastal zones. So Deborah started working on this topic back in 2005. She published a paper, and she kept working with some of the same people to refine this product over time. Whereas in the past, we'd take, so what we were, interested in is basically how many people are vulnerable to sea level rise. That's a basic question. Like how many people by country, by region are vulnerable to this and, or exposed, I should say, maybe not vulnerable, but exposed. And the early versions of this data product just use one elevation layer. So we know there's uncertainty in elevation. We know there's uncertainty in the population distribution based on these different gridded products. Some of them use remote sensing to redistribute the population. Some of them don't. So what we did was we basically said, let's look at the multiple elevation products. Let's look at multiple population products. And also there's an interest in whether people are in urban or rural areas. So let's look at multiple definitions of the urban and rural area. And that's what this version of the data set represents. Version 3 is that it has multiple input layers so that people can have a better sense of the uncertainties in the outputs. A colleague of mine, a former postdoc, was very involved in some work related to exposure to extreme heat. This topic has become, extremely important recently. As you probably saw in the news, 2024 was the warmest year on record. And it seems that we're having one warm year after another, and each year that comes along seems to be the warmest yet on record. I will say I'm not a climate scientist. I work with a lot of climate scientists, but I think a lot of the climate scientists I work with are actually somewhat surprised. They didn't expect this kind of warming effect so quickly. But as this happens, there's also a real concern about extreme heat and how it will affect human populations. So the measure here in this map here represents the number of days over the period 1983 to 2016 that heat exceeded the threshold. And I'm not actually confident in this image which of the thresholds it exceeds, but we'll just say for the sake of argument that it's 2-day or longer periods where the daily maximum heat is greater than 40.6. Though what Cascade tends to use and what he prefers to use generally is wet bulb globe temperature. That's that hot, humid heat that's really disagreeable in the summer. that's above 30 or 32 degrees. So that may be what this image represents. But the point is that there are different thresholds. There's no one universal threshold that's considered to be an absolute definition of extreme heat exposure. But as humans are exposed to more and more of this, it's going to become more and more problematic. And one region of the world that's also sort of stands out is the subcontinent of India, but also parts of West Africa, where in the Arab Peninsula, um, Arabia, that these areas are going to see a lot of very hot and have seen a lot of very hot extreme heat. We also do a lot with sort of remote sensing derived air pollution metrics, and I'm going to show you some of these in a mapping tool along with the heat measure. So we'll come back to those in a little bit. But this map here shows changes in PM 2.5 from 1998 to 2019. And the purple areas are areas that are seeing generally increases in PM 2.5 exposure. This is that fine particulate matter that's really bad for the health because it lodges deep inside your lungs. And so PM 2.5 or particulate matter at 2.5 microns is considered to be one very important health related threat for humans. And so you can see parts of the world are seeing pretty large increases in PM 2.5 exposure, Eastern Africa, Northern Australia, particularly the Ganges Basin in India and some parts of China, which are getting cleaner but are still seeing pretty bad declines. Fortunately for us, those of us who live in the Northeast US, you can see that the air has actually cleaned quite substantially and has gotten better over time, along with Europe. So this is sort of the tale of two worlds. This area in the Northwest, obviously, those of you who've tracked the news know that fire hazards have grown in significance. And so every summer, it seems there's a pall or a haze over much of northwestern US owing to forest fire activity. And not only do we have a global view of PM 2.5, and we're about to release a more recent version that goes up to 2023, I believe, or 2024. But we also have a US-centric version that has much higher resolution and is very useful for health studies in the US. So one of the things that people have begun to wonder, like when you have all these different population grids, which one should I choose? Should I choose should I choose the one that's modeled with a lot of remote sensing inputs, or should I choose the one like GPW that just takes the basic population? There is an article that describes the differences between these. Very briefly, what I might do is just show that there's also a web mapping tool called PopGrid. And PopGrid is this website that, and I'll be sending these slides out afterwards, but the PopGrid mapping tool we developed under funding from CDAC. And basically it has a 4-panel viewer in which you can look at, the population in different parts of the world, the urban population, in this case, degree of urbanization. You can look at population numbers, and you can look at the change over time in nighttime lights, which will suggest, see if I can pull up the legend here. So the more recent lights in this time period that's being studied is from 1992 to 2013. The red areas would be kind of new lit up areas. So the red areas around Accra and Ghana here are basically showing how that urban expansion is occurring over time. And so you can bring up, any number of different layers here and look at, this is our gridded population of the world. And one of the things you'll notice if you look at closely is, sorry, this is world pop. It's another, our gridded population is up here. My bad. So let me bring that up. You'll see how different these two are, because what we do with gridded population of the world is we use the administrative units that the data are reported in. And in some cases, those units are pretty coarse. So when you look at the area around Cotonou and Benin, or the area around Ghana, Accra and Ghana, basically what you see is the products that map population using remote sensing are able to provide a much more refined view of where the population is, and also many areas that are unpopulated entirely that would be useful to know about. So any number of the products that use remote sensing, you can bring up another one, will typically show you, a much more refined view of where the population is. Also, you'll notice that as we zoom in, you can see much more clearly areas of new lighting that occurred subsequent to 2002. So those would be areas that are new settlements that have occurred. If you go to the this upper right-hand button, you go to a tool that, if we zoom in the same area roughly, and draw just a simple rectangle, you can essentially get population estimates across all the different population grids. So that gives you an idea of the uncertainty again in the numbers and the counts in those areas. That would be important, for instance, if you were planning a humanitarian intervention in an area, let's say there were flooding or something like that, you'd want to know the range and estimates of population in order to be able to provide water, food supplies, and other things to populations that were displaced. So one thing that you can do with this tool is you can actually upload, you don't have to rely on these little drawing tools. You can actually upload the actual extent of, say, an earthquake area or something like that, and you'll be able to get the return on the number of people living in those areas. All right, let's go back to where I was before. And I hope I'm not being too long-winded. I want to respect everyone's time. I think, Mike, we have until 12:30. Is that correct?
Yes.
Okay. And if it's lagging or anything, Mike, just tell me it's lagging and I'll pick up the pace. Another area that we sort of got into as a result of our expertise in settlement mapping and population mapping was a whole development intervention area that is funded by the Bill and Melinda Gates Foundation, where we spun up essentially an activity that has now resulted in quite a bit of funding. It rivals CDAC, not quite at the same level, but it's still pretty big, for mapping in Africa populations that are in remote areas in particular, but generally just getting better population and settlement maps. The reason for this is that Gates Foundation would go out to the field. Some of you are aware, Bill and Melinda Gates and the foundation were very interested in health-related interventions, particularly polio vaccination campaigns. In more recent years, it was COVID and COVAX effort, vaccinating the world's population for COVID. And they didn't know how many people were in a lot of these villages because the maps and the base information in each country was so poor. You might have an order of magnitude greater number of people in an area than was expected when you got out there to do the vaccination. Well, if you're shipping vaccines out to some remote area, they have to be stored in a cold there's something called cold chain, which is basically the vaccines need to be kept cold and refrigerated the entire time. It's a tremendously expensive operation. And if you get out there and you only vaccinate 10% of the population because your population base maps are so poor, that actually puts the remaining population at greater risk. And it really doesn't stem the spread of these diseases. So they have funded us fairly heavily to get better data in places like Nigeria, Congo, and a few other countries like Zambia. And these have been used now for extensively, not just for vaccination, but a lot of other health-related responses. Here's a map of the areas that Grid 3 has been involved in operating in, and several of our staff are working in Grid 3 now. The former deputy director of CIESEN, Mark Levy, was the one who kind of came up with this approach, and he's now spun off and become the head of Grid 3. Other areas that we've been involved in through one of our new, relatively recent colleagues is slum mapping and mapping people who live in disadvantaged communities in low-income countries. She calls it slum mapping. Some people don't like the term slum. So she'll also say very quickly that informal settlements is what they're really talking about, people who are living generally without legal right to their land and who suffer various deprivations as a result. Well, she developed this also with Gates funding, and this Idea Maps effort has really taken off and been able to produce a lot of useful data for local planning activities in many low-income communities around the world. Project that I've been involved in almost since I began, really since I began at CIESEN, is national level comparative indices or indicators. These are composite indicators that are intended to be able to provide, a comparative view of comparative metrics on things like um, climate change in the country efforts to tackle the issue of climate change and emissions, ecosystem vitality, biodiversity conservation, water bodies and preservation of water bodies, agriculture, and then a whole area of environmental health. So this is just a zoom in on the middle of a larger wheel that shows all the individual indicators that go into this. But this has been going for 20 sorry, well, the EPI has been going for about 20 years. Before that, we did something called the Environmental Sustainability Index. There's a really cool mapping tool. So if we have time, we'll get back to it later, but it's a tool that you could use in the classroom to basically explore country scores. And so we'll get you that. I'll show you that tool in a little bit when I do a few demos. This is an example for the most recent EPI. This is the 2024 EPI, and the countries that are at the top, often dominated by a lot of wealthy European countries, and the countries that are at the bottom, which are generally speaking much poorer countries with much lower levels of environmental regulation. And so, the idea, in part, the device of ranking and the device of creating these indices, I think is, it's intended to basically set up a competitive dynamic where countries actually care where they rank and they make a double effort to try to improve their environmental policies and conditions for their population. And it has worked in that way in some countries. I will say that it doesn't work in all countries, but there are countries that take up the challenge and have really made improvements. South Korea being one that early on got very poor ratings for air quality and some other metrics. And we went to visit South Korea about 15 years ago, and they had made major strides to improve the air quality for their population. So that sort of covers a number of our data products. I'm going to talk a little bit more about the area of research that I'm most involved in, which is climate-related vulnerability and climate migration. So this is a recently funded effort that we completed this last year in 2024, where we basically map past and future likely climate impacts in urban areas. And this was led by the same woman I mentioned, Dana Thompson, who was involved and is involved with the Idea Maps Consortium. So she understands a lot about what makes urban poor areas vulnerable. So she was also very skillful in using available data sets and being able to accurately map those areas of a city that are lower income. So this is an example of an approach that was taken by a group at University of Chicago to map low-income neighborhoods based on the degree to which they're serviced by roads and other infrastructure. So my understanding is the yellow areas are more deprived. Some of this is in Nairobi, and it's an area called Kibera, which is a well-known slum in Nairobi. But she took that methodology, refined it, and came up with maps of urban slum or low-income areas for all low-income countries around the world. And then what we did was we looked at the exposures, the multiple exposures for those urban slum areas that, the ways they're being impacted by extreme heat, by flood risks, by sea level rise, by I think there were just a number of other areas that we covered, air pollution as well. And if you'd like to learn more, I have a whole separate presentation, and I could do that if we still have time. just go through some of those slides. This is the work that we started on in terms of getting us going in a whole area of work where we were projecting future climate migration. But to do that for this particular project, Groundswell, which is funded by the World Bank Group, we first had to model future population distribution. So I'll describe why we had to do that and how we derived migration from that effort. But if you've seen the number, 260 million people may be displaced by population internally within countries by 2050. That's been widely reported in the media, and the source of that is this work that we led at CIESEN. So another project that was a spin-off in a way, was using the same model but focused only on Africa, was with an organization that we've now essentially established a partnership with. It's the Global Center for Climate Mobility. And they asked us to use a similar model to model future population distribution and migration in Africa. And the person who led this work is actually at CUNY, CUNY Baruch. It's a college of CUNY in the city, and he's specifically at the CUNY Institute for Demographic Research. So he developed a model that I'll describe in a second. The ACMI report won a Webby, and the website won a Webby. It was quite well designed. These are, the way that the ACMI work, or the Global Center for Climate Mobility works, is they really try to target policymakers at the highest level with information that they may need to plan future adaptation efforts. And in some ways, you could say that if climate change impacts are as bad as some people predict, one of the leading indicators that we'll see is whether people actually have to leave an area or not. And that's a little binary, and I'm simplifying things grossly, but you could say that if adaptation fails, then likelihood is that people will need to move out of certain areas. And that's sort of the thinking behind these report series. What you can see in Africa, for instance, is that a high percentage of people actually have thought about moving. Now, in the US, we're a highly mobile society, and that may not be surprising that 45% of the population would think about potentially moving or may have already moved as a result of, for whatever reason, economic opportunity or those sorts of things. But it is a very high percentage of the population that's considering and it may aspire to move. So how did we do this? How do we project future population distribution, and then out of that come up with future migration? And so it all comes back to gridding, right? So I talked about gridding earlier, and why do we grid the world? Well, this is a gridded population data set that we use for the ACMI, the Africa Climate Mobility Initiative. It's actually a modeled population distribution. So I showed you the difference between a modeled surface earlier and one that just uses the raw census inputs. And you see that, the population looks a lot more focused in certain urban and heavily densely populated areas. So what we start with is we start with projections that only use development scenarios. So these are basically scenarios that say urbanization is going to increase by X%. Education levels would be thus and so. And they're called shared socioeconomic pathways. It's a way of thinking about the future in storylines. And the storylines differ. Some of them are like, this is an ideal storyline for future development, low population growth, sustainability, much better economic prospects for the population, better education. And then there's other scenarios that are considered to be more pessimistic, where results are that people are less educated, population growth remains very high in places like Africa, and urbanization rates may, in fact, be lower in some cases because people are sort of trapped in rural areas. So these form the basis of one scenario, and then what we do is we add climate impacts on top of that in ways that make some areas more attractive and other areas less attractive based on water availability, crop production, and grazing resources. And when you subtract one from the other, basically you get a difference between the climate scenario and the no climate scenario. And those differences we attribute to migration. So if, in this case, areas that are uh, in, pardon me, are in red represent in-migration areas, new places where there'll be new migration into. So you can see this population density is darker here and this and therefore higher in the climate scenario. And then in the climate scenario, there's also fewer people in this northwest corner. I'm just imagining this country as a fictitious gridded country with 15 by 15 kilometer grid cells. So that's what these grid cells represent. And so you can do this for whole countries. And what we did, in fact, do for every country in the low income world and every country in Africa. And basically, what you see is areas that are in red see increases in population as a result of climate impacts. And areas that are in blue see declines in population as a result of those impacts. And when you sum up all the red grid cells, because the blue and the red will essentially subtract or they will zero each other out. When you basically look at the red areas alone and summarize, you get a total number of migrants and add up all those red grid cells. And in Senegal, under a business as usual, fairly pessimistic development scenario, you see over 1.2 million people are likely to move with some uncertainty because we use different scenarios, different climate impact models to model this future world. All right, so then the same data set now, these data sets are now available because we want to make these data freely available through the portal, the CDAC data website. So you can go to this URL, you can actually download the data. If you're familiar with GIS, you can actually analyze the data. These are hotspot maps that we produce for the groundswell report showing areas where there's high certainty of migration into areas in red, excuse me, high certainty of migration out of certain areas in blue. And these are this is sort of the summary chart that is used in groundswell to show the numbers of people moving. And you could see the high end. Sorry, I misstated. I think the high end is around 216, not 260 million. And the low end, though, is around 50 million globally. So this means for all these countries in black here in this map, that the range in future migration, internal migration as a result of climate change could be anywhere from roughly 50 million people all the way up to 216 million people. Unfortunately, the media very rarely cites both the high and the low end. They usually just focus on the high end. We've then moved on to do modeling in the Caribbean region. For this work, we actually switched to a different type of model that uses changes in economic productivity and where people are assumed to move from low wage areas to high wage areas given a certain threshold. And so this is the new work that we're doing that's just being released now on the Caribbean region. It includes all countries in the Caribbean, including every country that borders the Caribbean is included, except for the United States. It does, what I will say is one other thing is in the groundswell report, we very much focused on internal migration. In this report, we're actually looking at both internal and international migration. If you're alarmed or worried, well, the numbers are not that terribly high, and I have a separate presentation on this as well. So if you really want to dig into it, we can go there. Last kind of research project I'll describe is some work we're doing with funding from the Department of Defense, DoD. They have a basic social science research program called Minerva. And since I have a lot of experience in West Africa. I was a Peace Corps volunteer in West Africa. I worked there for many years. I was in and out of the region for many years, I should say, not work there. I did my 2+ years in Peace Corps and then I left, but then I would go back and I would do work-related trips for various purposes. So I have some familiarity with the region. The other region is Central America, and that was because a close colleague of mine has a lot and deep experience in Central America. And so we decided that these two regions, which are large migrant sending regions, to the global north. So, a lot of people from Central America end up in the United States. Increasing numbers of West Africans are going to Europe, and they're often following very perilous journeys, right? There's human smugglers who are taking them on their way to the frontier, to the border. They have to get on boats if it is to traverse to the Mediterranean, but first they have to cross the Sahara, or they need to go up the coast. Both are very perilous journeys. There have been a lot of deaths in transit. I recently got an Uber ride from a gentleman who described his trip from Nigeria down here across the desert all the way to Morocco and eventually to Spain. He said he was held at gunpoint at various points. His best friend was stabbed to death. And when he got to the water and took a boat across to Spain, the boat capsized and his arm was broken because someone was grabbing a hold of him so strongly. If you've ever been with someone who doesn't know how to swim and they're drowning, it's a very dangerous situation. And the only way he could save himself was to basically get away from this person as strongly as possible. And as a consequence, he broke his arm. He said it was a very hellish journey. And we've heard many other anecdotes and stories from people who traveled across Mexico and through the Darien Strait down here. These are extremely perilous journeys. So the question behind all this is, why are people moving? What's driving them? What are some of the issues? And so we're looking at the issues with a particular interest in climate-related drivers, but we recognize full well that actually climate factors are a relatively small contributor to the stresses that people face. And a lot of people are just seeking security in a more stable environment in which to raise their kids, a future, a hope. So these are some of the numbers of people who are caught at the border. These are from the Customs and Border Patrol, and in this case, it's from Central America. And these are the number of unaccompanied minors, meaning people under 18 years of age who are traveling on their own or in families. And you can see a very precipitous rise in the number of unaccompanied minors leaving the region. This is the kind of COVID trough right here, and then it's picked up again since then. Frontex data tell a similar story. This is data at the European border of the European Union, and the numbers really peaked in the mid-2015s, and then the governments of Europe basically cracked down and sought to keep and interdict any boats that are coming across the Mediterranean, so those numbers declined somewhat. But you can see some real spikes there. And so part of our work has also been to look at the underlying agricultural conditions and climatic conditions in these regions. One thing we noticed was a strong decline in precipitation in the July months when it's the middle of the growing season in Central America. And this results in what's called the canicula, or the midsummer drought, which can really drastically affect crop production. So food security, food production, tied up with climate, tied up with economics, tied up with often very dysfunctional governments, tied up with narco trafficking and gang-related activity in these countries of origin, are all affecting people's decisions to migrate. And we're still in the process of sort of doing a fuller assessment of the survey data on migrant motivations. I'll close a little bit just talking a bit about our work on open and participatory science. We've been very active. We have collaboration with Lehman. Now it's with CUNY more broadly, where we're getting students in from different college campuses that are part of CUNY. And they're doing internships with us to learn more about GIS and the tools that we use in our work. And we've had trainings for students in Colombia, for instance, and we've had a lot of work on training people in low-income countries in different areas. And we have a project that is winding up this coming year, but basically is looking at developing curricula. So these are curriculum largely for college level students that are intended to help them address questions around using open source tools, Jupyter notebooks largely, around water resources, health and air quality, environmental justice, disasters, wildfires, etc. So each of these modules will come with a number of data sets that are useful, and they're teaching the students how to use these open source tools with often cloud-based data. So data that you can just use in their native cloud format, and processing the data in ways that give you answers to certain questions. So that's a recent effort. And then I've been involved very heavily in efforts to document the importance. Well, I'll say heavily as in quotation marks, but I've been involved with work that has sought to document how important it is to have citizens involved in data collection and the ways in which we can do a better job of preserving the data that are and ensuring high quality data out of citizen science. I don't know how many of you know this, but CUNY has actually been awarded a NASA grant called GLOBE, and it's for data, it's for use of earth science data in the classroom. So let's take a look. I already showed you the PopGrid viewer. I don't know if yeah, we did get the different populations, right, for that area. So let me get rid of that. There's the natural hazards mapper. This tool is going to be deprecated soon, meaning we're no longer supporting it. It's partly because NASA has decided that we're no longer going to do, what's the word? We're not going to have individual data centers developing their own tools, but everything should be an enterprise level tool. So in a moment, I'm going to show you what those enterprise level tools look like. For now, what I'm just going to show you is that this tool that we developed basically integrates things like fire activity, aerosol optical depth, flood outlook for the US. I'm not sure if there are any current floods right now. So, but if they were out there, you would see a little polygon showing where the floods are, the flood warning areas for the US. What you can see is, some of the wildfire activity out in the LA area. I'll show you another tool that NASA has that also enables you to do some of these explorations. And so this is today's situation. The tool that I'm going to show you at NASA allows you to look at the situation over time. But one thing you can do is get a sense like, okay, let's say you knew the exact area of Palisades, where the Palisades fires occur. You could click around it. Okay. Well, in theory, you can click around it and get a return on a population estimate. I think that because we're migrating a lot of these services, some of them actually may not be fully functional now. So for that, I apologize. But normally what you get is a population count here with an age structure. The population estimation service here gives you essentially the same capability. You just don't have the overlay of the hazards. So let's just do that quickly for this area of the Palisades. I'm kind of guessing because I don't know where Palisades is. I'd have to bring up a map. But what you will get is essentially the population and a pyramid, age pyramid. So this shows you what the population is, roughly 60, it's kind of hard to read, 600,000 people. And for one time slice, you can get the age distribution in 2010. And we're doing, just to make it clear, we're working very actively on getting the 2020 population, the census rounds from 2020 gridded. It's just that it takes a fair amount of time because the censuses are not all released at the same time. So this gives you an idea of the age structure. What does this age structure tell you about the population in the Palisades area? Let's just assume this is Palisades. Anyone want to hazard a guess?
Can you make it a little larger, please?
Not sure I can make it any larger. I'm sorry about that. The base of the pyramid is the 0 to 4, and then it goes all the way up to 65 plus. So what this shows is essentially, and you can click on any one of these to get the population in each age band. But what it tells you is essentially that this is a much older demographic in this area. There's, the pyramid is almost like an inverted triangle with a lot of people at the highest ages. So this must be an area that I assume is attractive to retirees because it's near the coast. If you compare it to
It's old
some,
movie stars.
what's that?
Old
Movie
movie
stars.
stars.
Yeah, they're all movie stars with extensive plastic surgery. Um, just kidding. Sorry, I didn't mean to slight
We
anybody.
we have a raised hand, Michael after Eve.
Yeah, Michael, tell
Oh,
me.
yeah. Is this going to be on the final slide? Is that where I can access all of this?
Yeah, so these tools are all on the final slide. I'm going to show you that final slide just so you know what you're going to look for. I showed you the hazards mapper. Here's the population estimation service. Okay, so you can go to that link. Now, I just showed you the population pyramid for the part of Palisades. This is across the border in like Tijuana, Mexico. What does this tell you about the population of Tijuana?
A
Mostly
lot
young.
more younger, yeah.
Yeah, good, Michael. So the two mics. So yeah, I mean, you've got a lot more, proportionally, a lot more people in the young age groups. And if you went to a really poor part of the world in Africa, you would see an even more stark pyramid where it actually looks kind of like parabola. Okay, so these are just some telltale signs you can look for when you use the tool. And you can pan and zoom. So I'm zooming out, and you can do the same. Maybe I'll just test Africa, see if I can get results quickly enough. Sometimes the tool is a little sluggish, but it seems like right now we're doing okay because there are not a lot of people probably tapping the tool on a Saturday morning. So this is the pyramid you can see the growth rate, first of all, much more dramatic growth in Africa over time in population. And then hopefully I'll be corroborated and the pyramid shows just how many people are younger. So yeah, just a lot more of a traditional pyramid. All right, so let's go to the next tool, which I had on my list, which is this tool called Worldview. So this tool is sort of an easy access tool that NASA has developed for people to be able to access their data. And a lot of the data that they provide is near real-time data, meaning it's not been heavily processed, but it is, reasonably accurate. And so what I thought I'd do is just show you a couple things. Now, this is the thermal anomalies. So again, zooming in a little bit more on the area around in LA. So this would be areas that have there are likely fires or maybe gas flaring or other things that remote sensing can pick up. But in this case, it's probably fires. And I already added a couple layers here. One of them is the population density layer. So right now I don't have it shown, but if I click off here, it shows the population layer. Great. Well, not so great because I can't see the fires now. The fires are red, the population is red. What can I do about that? So if I go in here, I can go to view options and I can choose a blue map instead of a red map. And so this could be an interesting tool for students to look at. And then you can actually click through. So the fires, I was told, started on the 7th. Or I was told by Google, sorry. Nobody actually told me. I did a search. So this is we're on the 5th. You can see down here in the bottom corner, 6. And then suddenly you get this huge increase in fire activity on the 8th. And it continues on the 9th, 10th, 11th, and then the fires, start to be extinguished. So unfortunately, with this tool, you cannot do any calculations about the number of people. You can, from my understanding, you can actually download data using the tool, but I haven't tried that. So that's that. And if you wanted to add layers, let's say, you know, I'm interested not only in the fires, but I'd like to know like how many aerosols are in the air. Meaning aerosol optical depth is a good measure, for instance, of of fire related or smoke. So this has already been added. Maybe I'll try one more just to see if I can compare the different products a little bit. So I'm going to click off, and now we have, for instance, this new product called Deep Blue Aerosol Optical Depth. It also should have the ability to go back in time. So let's look at, and the thing about this is it will show areas, for instance, if there's cloud cover or something else you were not going to be able to pick up. That's why there's these big gaps. But you begin to see the amount of smoke. Fortunately, the prevailing winds at the time of the fires were going out to sea. So a lot of that smoke, you know, is concentrated, you know, in the ocean and also some of the islands offshore. But this gives you an idea of the plumes over time. And, you know, that's one example. There's other examples that, let's just turn off these layers. I looked at a few other examples. These are all base layers, I guess. Yeah, so I think this is another example using a different instrument. So you can learn a little bit about the instruments online as well and find out what difference there is between MODIS and, for instance, this one that I had up earlier, which is the Deep Blue from an instrument called VEERS. So these are just different remote sensing instruments. Okay, so that's the sort of intermediate product in the sense that it's easier to use, fairly straightforward. You can look at your whole set of natural hazards, or you can look at it by science disciplines. A number of our data sets like dams and things like that. But let's look at flood hazards. So I'm just looking at what they have for flood. These are mostly look at hazards instead. Ash plumes, fires, dust, drought. Anyway, I thought they had a flood. Oh, here it is, flood. So, you know, flood hazard. And so you could add different things in here. Precipitation rate. Go back to flood. Flood. So like, I don't even know some of these. I haven't looked at them, but you could start exploring these different data products to get a better sense of what they represent. And it's, you know, fairly just visualization focused, but there are some pretty cool things you can do with a time series. You can really look at how things have changed over time. Because it's a near real-time product, these are not stitched together swaths. This represents essentially the way the satellite is coming down over the North Pole. These would be polar orbiting satellites, and they take swaths, one swath at a time, and they measure what's going on within those swaths. You can get more information about the different products by just clicking on the I button and finding out more. Let's see. The other tool that's on my list and which you'll see is the Earth Data GIS. This one requires a bit more knowledge of how to use GIS, Geographic Information Systems. And I pulled up a few layers already. This is not where you will go to find the most recent fire activity or the most recent flood-related activity. This is where you might go to find things that are more long-term. So one thing that I did was just go to the layer search tool. So if I want to search for layers, wait a second. I had it up earlier and I don't. Oh, so here, it's at the very bottom. So you click on add and it'll give you a search box. And then for all of our data products, basically, if you just click write CDAC, you can get all the products, some of the products that I already described to you earlier and many more that are, potentially of interest to you. So, here's a global product that talks about urban access to public transport infrastructure. So I'll add that, but I don't have to wait for it to load. We can go back to the layers that I have already displayed. So I'm going to turn that one off for now, and let's look at something that might be of interest to some of you in the New York area, for instance. Let's look at low elevation coastal zone in relation to population distribution. So what you see here is large areas of the Southeast United States and Florida and stuff that are affected by and that have large areas of low elevation coastal zones. Well, what do these zones represent? Let's take a look. For the symbology, it's over here. You have to go to the properties label, and it tells you 0 to 5 meters, 5 and 10 meters and above. So this would be up to about 15 feet in elevation and 15 feet to about 30 feet in elevation. And you can see large areas of, New York City and Long Island that are potentially affected, Jamaica Bay. Let's make the transparency of this a little better. So now we see it, now we don't. The transparency, I think I can manipulate here by changing the transparency. So I'm making this layer more transparent so I can see how many people, what the population distribution is underneath that layer. So that's just an example of a way of overlaying two data sets to get a kind of sense of the exposure of the population to sea level rise. Let's turn off this layer and I'll show you another that has another feature to it. Maybe I'll turn off population as well. Come down here. Earlier, I loaded the PM 2.5. It takes a moment for these things to load, so you have to bear with it. This is fairly coarse and doesn't give you a lot of distinction for the Northeast. It's binned. Binning means that we take the data and we put it into different bins. So this would be the legend here. In areas with in yellow are basically considered to have adequate air quality, but the real desirable levels of air quality are in the 0 to 10 bins for air quality in the PM 2.5 data set. But if we think we have it kind of bad with the 10 to 20 parts of the world, like in China and in the units are much higher. You can click on any pixel and get the value. So in this case, way up here, the value is 175 micrograms per cubic meter. It's considered particularly high levels of concentration. This is the data set I mentioned earlier, global extreme heat. And if I click over here, and it brings up the new legend, and it tells you the number of days that exceeded the heat threshold. One thing I need to do is work with my team to make sure that the threshold is made very clear. We need to tell people the threshold is thus and so temperature. And so I'll be working with them to make sure that we get that in there. One of the nice things about this data layer is if I take away the legend, is it has a time series. So you can see how extreme heat has sort of changed over the years. And so the slider, I think that if you click, I don't know if it, yeah, automated. So that gives you an automated slider basically showing you the changes in extreme heat exposure. So that's just something to, you can play with. You can make I guess you can make it down to 1 year. I'm not sure if it changes the values. I have to double check that. So I just clicked on a pixel. It may be that when you have the time slider up, you can't click on values. You can only do one at a time. So this would mean that 189 times this particular threshold, probably at 32 degrees wet bulb globe temperature, has been passed in this time period from 1983 to 2016. So that's a lot of times. It's also quite a number of years, but it's not insignificant. Well, thank you so much for your attention. I appreciate it.